What do this double pendulum and changing an event in your life have in common? Whether it is never having confessed your feelings to someone, turning down an important opportunity, or simply having been present at a key moment that led to a friendship, what impact would such a change have had on your life? The link between this double pendulum and that change can be summed up in one word: chaos. Chaos is not simply disorder. It is the moment when a world that runs like clockwork nevertheless becomes impossible to predict. And it's precisely this paradox that makes it so fascinating. When people hear the word chaos, they generally think of something completely messy and confused. In everyday life, that is indeed how we use it. A messy room, a crowd running in all directions, a situation that escapes all control, we say it is chaos. But in science, the word has a much more precise meaning and above all, a much more surprising one. Chaos theory is not about a world without rules. On the contrary, it deals with phenomena that obey very strict rules, but whose evolution becomes so sensitive, so complex that after a certain amount of time, we can no longer predict them correctly. And that is where the most unsettling idea lies. A system can be perfectly deterministic without truly being predictable in the long run. That's the case with the double pendulum. And the fact that a system can be perfectly deterministic without really being predictable is essential because we often confuse three different things: disorder, randomness, and chaos. Disorder, first of all, is an impression. It is what you feel when you do not see any clear organization. Randomness, on the other hand, refers to something whose outcome is not fixed in advance in any simple way, like rolling a die or drawing lots. Randomness is more mathematical. Chaos, however, is something else entirely. In a chaotic system, there is not necessarily randomness in the strict sense. The system follows rules. If you knew its exact initial state, and if you could measure everything with perfect precision, then in theory you could calculate what would happen next. But in practice, that perfect precision almost never exists. And it is that tiny gap between what the system truly is and what you think you have measured that eventually becomes enormous. To visualize this principle without using the double pendulum, let us take the example of the break shot in billiards. Granted, it is not the cleanest mathematical example, but I would say it is a good analogy. The cue strikes the white ball, which then hits the triangle of balls carefully arranged on the table. At first glance, everything obeys very clear physical laws. The angle of the shot, the force, the rebounds, the friction, the collisions between the balls, nothing is left to chance. And yet, a very small difference at the start, a barely altered angle, a slightly stronger or weaker force, a point of impact shifted ever so slightly, can completely change how the balls scatter across the table. At first, the difference seems insignificant. But after several collisions, it becomes enormous. The balls no longer end up in the same places at all, and the rest of the game can unfold in a totally different way. That's the heart of chaos theory. In certain systems, tiny differences at the start can produce major differences in the outcome, even when everything is governed by well-defined laws. This idea can be difficult to accept because for a long time science was associated with prediction. To understand a law meant being able to announce what was going to happen. And that is true in many cases. If you gently throw a ball, you can estimate where it will land. If you heat water, you know it will eventually boil. If a planet orbits a star under simple conditions, you can calculate its motion with very high precision. This success of science created the impression that the entire universe worked like a vast, well-regulated machine, and that observing it correctly was enough to know what would happen. Chaos theory does not destroy that idea, but it complicates it considerably. It shows that there are systems in which knowing the laws is not enough to predict far into the future. And this is where a very important nuance comes in. A chaotic system is not an incomprehensible system. It is often difficult to predict, but it is not absurd. It does not do just anything, it follows a logic. Except that this logic produces extremely sensitive behavior. Chaos, then, is not the absence of order, it is a particular kind of order. An order that can generate unpredictability, not incomprehensibility. And all of this forces you to admit that there are limits to prediction, even in a universe governed by laws. That doesn't mean science has failed, it means that understanding a phenomenon and predicting it perfectly are two different things. You can very well grasp the general mechanism of a system without being able to state precisely what its long-term state will be. For example, you can understand why the weather changes, know the major laws of atmosphere, understand how warm air and cold air interact, and still remain unable to predict with certainty the exact weather several weeks from now. That's not because the atmosphere obeys pure randomness, it's because it largely belongs to this family of systems in which small initial differences become enormous. Sensitivity to initial conditions is the main property at the heart of chaos theory. And it's generally when this sensitivity is discussed that the very well-known image of the butterfly effect appears. It's often summed up by a striking question. Can the flap of a butterfly's wings trigger a storm on the other side of the world? Taken literally, this phrase may seem exaggerated. It gives the impression that one small isolated gesture single-handedly creates a gigantic event. In reality, this idea is subtler. The butterfly's wing beat does not create the storm out of nothing. Rather, it represents a tiny variation in a system that is already extremely sensitive, such as the atmosphere. If conditions are such that this variation is amplified all the time, then the final outcome may indeed be very different from what it would have been without it. So the image does not mean that one tiny event will necessarily produce some immense catastrophe. It means that in certain systems, very slight differences can profoundly alter the overall evolution. It's an almost disturbing idea because it challenges our intuition. We like to think that there is a simple proportion between causes and effects. A small cause would produce a small effect, and a large cause a large effect. In many cases, that's true. If you gently push at all, it opens a little. If you push hard, it opens wider. But chaotic systems do not always follow that reassuring logic. They are made of loops, interactions, feedback, and chain reactions. What matters is not only the size of the cause, but the structure of the system in which it occurs. A tiny variation in a highly sensitive system can become enormously important, whereas a much larger variation in a stable system may have no major consequence. This also helps explain why prediction has a natural limit in certain fields. Let us take weather, the most famous example and one we have already mentioned. Forecasts are often good a few days ahead. They already become much more fragile after a week, and beyond a certain horizon, uncertainty grows considerably. Yet, the physical laws of the atmosphere do not change according to the mood of the sky. They remain the same. The problem comes from the fact that the atmosphere is the vast, mobile, highly sensitive system in which countless variables constantly interact. Temperature, humidity, pressure, winds, terrain, oceans, clouds, all of this forms a whole in which small measurement errors spread very quickly. Even if you have powerful computers and lots of data, you can never completely eliminate the initial uncertainty. And in a chaotic system, that uncertainty always ends up taking over. But one confusion must be avoided. Saying that a system is sensitive to initial condition does not mean that it reacts in a totally disordered way to absolutely anything. There is structure, there are limits. Not everything can happen. For example, a region weather is not suddenly going to produce absurd temperatures or violate the laws of physics. Chaos does not remove the overall framework. Above all, it makes precise long-term prediction impossible. That's an important difference. The system retains a coherence, but that coherence is not enough to lock the future into a single trajectory that we could follow without error. At bottom, this sensitivity to initial conditions says something very profound about our relationship to reality. It shows that the world is not difficult to predict only because it is complicated or because we still lack good theories. In some cases, imprecision is part of the game. Even with known laws, even with sophisticated tools, there is a boundary beyond which detailed prediction becomes blurred. As we have seen, for a long time, many scientists believed that if one knew the laws governing a phenomenon and its initial conditions well enough, one could predict its evolution without too much difficulty. There were good reasons for that idea to exist. After all, it had worked very well for describing the motion of planets, the fall of bodies, and many other physical phenomena. Then, in the 20th century, a shift occurred. Researchers began to see in certain calculation behaviors so irregular that they seemed almost absurd. At first, one might have thought there were calculation errors or machine defects. In reality, they had stumbled upon something much deeper. Chaos theory was born at the moment when people realized that perfectly deterministic laws could produce evolution that were impossible to predict in detail over time. The name that comes up most often in the story is Edward Lorenz, an American meteorologist. In the early 1960s, he was working on weather prediction with a very simple computer compared with those of today. His goal was not to revolutionize all of science. He mainly wanted to better understand how the atmosphere evolved and why weather forecasts eventually lose reliability. To do this, he used a reduced climate model with only a few variables in order to simulate the behavior of the Earth. It was in this context, in 1961, that he made a discovery that would become famous. The story has remained famous because it is so simple. One day, Lorenz wanted to restart a simulation he had already run. But when he re-entered the numbers from the first simulation using the 3 decimal places shown on the printout, he forgot that the computer had actually performed the calculation using 6 decimal places. So he entered a rounded value. When the machine started calculating again, the final results drifted further and further away from the first simulation. At first, the true trajectories seemed close, then they diverged completely. What Lorenz had just observed was the central idea of chaos theory. In certain systems, an infinitesimal variation at the start is enough to completely transform what happens afterward. This discovery was decisive because it showed that unpredictability was not necessarily due to complete ignorance or pure randomness. Lorenz's system did follow rules. It did not invent its motion at random. But those rules made the system extraordinarily sensitive to initial conditions. 3 extra decimal places that changes everything. And in 1963, Lorenz published a now historic article, often considered one of the great founding texts of modern chaos theory. Even though at the time it went somewhat unnoticed. It was not until 1972 that his work truly drew attention when he gave a lecture in which he asked the famous question, does the flap of a butterfly's wings in Brazil set off a tornado in Texas? That's how the butterfly effect became widely publicized. Lorenz's work thus helped explain why weather, even when studied seriously and with solid laws, cannot be predicted indefinitely in detail. It's also important to understand that this scientific revolution is closely linked to the arrival of computers. Before them, many calculations were too long, too repetitive, or too complex to be explored properly. Computers enable researchers to quickly repeat long sequences of simple operations and observe their evolution step by step. That's when a surprising phenomenon appeared. Relatively simple equations could produce incredibly rich behaviors. Without computers, many of these trajectories would have remained invisible. Chaos theory therefore owes a large part of its development to the fact that scientists finally had the means to watch systems evolve over a long series of calculations. And little by little, other researchers realized that what Lorenz had seen in meteorology was not limited to weather. Comparable behaviors were found in different fields: fluids, biology, certain mechanical systems, and even very simple mathematical models. Chaos theory was therefore not just a local curiosity, it revealed a general property of many dynamical systems. And importantly, it was also around that time that people began to visualize certain now famous forms, such as the Lorenz attractor. That looping figure resembling butterfly wings, which did so much to make these ideas more concrete. To be more precise, the Lorenz attractor is the shape taken by the evolution of a chaotic system when it is represented graphically. Edward Lorenz brought it to light while studying a highly simplified model of atmospheric convection, that's air movements linked to differences in temperature. By plotting the evolution of the system, he obtained a famous figure that resembles two butterfly wings. And even if the word attractor may sound strange, the idea is fairly simple. In many systems, the evolution does not fly off in every direction forever. It remains confined within a certain region, as if the system were being drawn toward a general shape. In simple cases, this attractor can be a fixed point or a regular cycle. In Lorenz's case, it is far more unsettling. The trajectory constantly circles around two neighboring regions, jumps from one to the other, and never passes through exactly the same path twice. So the system stays within bounds, but without ever stabilizing or truly repeating itself. That's why people often speak of a strange attractor. There is indeed a form of order, since the trajectories do not go just anywhere, but this order produces behavior that is unpredictable in detail. Two very close starting points will at first follow almost identical paths, then quickly diverge. And yet, despite that divergence, they both remain trapped within the same overall shape. What is fascinating is that this figure is not just a pretty drawing, it captures the central ideas of chaos theory. Unpredictability is not necessarily synonymous with total disorder. Lorenz's system obeys precise rules, but those rules generate an evolution that does not simply repeat itself and that depends enormously on initial conditions. The Lorenz attractor has therefore become a kind of visual emblem of chaos. In the end, if there is one thing you should take away from that entire video, or rather from chaos theory, it is that the world can follow very precise rules without therefore being easily predictable. It teaches us that unpredictability is not always the opposite of order. Sometimes it arises at the very heart of perfectly regulated systems, simply because they are extremely sensitive to the slightest variations. In that sense, chaos is not the negation of science. On the contrary, it reveals all of its subtlety. Understanding reality is not only about searching for laws, it is also about accepting that some of those laws make the future more fragile, more shifting, and harder to grasp than we once imagined. That's it for this video. If you need affordable YouTube thumbnails, feel free to order them from my Fiverr page. I'm trying to grow my little business so I can make a bit of money and reinvest it into the videos. So I will leave the link to my thumbnail making page on Fiverr in the comments, in the description, and at the end of the video. And otherwise, I sincerely hope you enjoyed this video. Don't forget to like, subscribe, boost the video, etc. And of course, see you next time.